In the previous classes, we have discussed about GCD and the theorem regarding the existence of GCD. So we'll further go forward with some properties of GCD. So before that, let us briefly recap. So before we discuss GCD, what are devices? Devices of a number are basically the set of all natural numbers which divides that number. For example, the devices of 6 are 1, 2, 3 and 6. So these are set of natural numbers which divides the number 6 itself. So these are called the divisors. Okay, remember that if 2 is a divisor of 6, we can write 6 as equal to some multiple of this 2. So okay, this is the idea of a divisor. Okay, so what do you mean by GCD? So when you're taking two numbers, what you do is that you take the divisors of m as well as the divisors of n and you choose out the common divisors, and the greatest of them is called the greatest common divisor. Okay, for example, GCD of 18 and 12 is nothing but 6. Okay, so we have also discussed one lemma regarding GCD, that is the GCD has a particular property that the intersection of the divisor set of m as well as the divisor set of n will actually be the divisors of D itself. Okay, so the intersection, the common divisors, the actual common divisors of both m and n will actually be the divisor set of D itself. That is a property of GCD which we had discussed in the previous class. Okay, now we will discuss the significance of this result by using the familiar Euclidean algorithm, how to find the GCD of two numbers. So we are going to find out, to discuss how to find out the GCD of two numbers. Okay, for that we are going to use the Euclidean algorithm. Okay, so before that, remember this. What do you mean by the GCD of m, a natural number m, and also a 0? Okay, so before that, what are the divisors of 0? Divisors of 0 are actually the entire natural numbers. Why? Because every natural number is a multiple of 0, right? So for example, 0 can be written as a multiple of every natural number. Why? Because you take a natural number and you multiply by 0, you will get 0 itself. So you see that this n will always divide 0. So every natural number divides this 0. That means the divisors of 0 are nothing but the entire natural numbers. Okay, now if you want to find out GCD of m and 0, you take the divisor set of m and you look at the intersection. What would be the intersection? Divisor set of m would be a subset of the natural numbers and divisors of 0 is the entire natural numbers. So the GCD would simply be the divisor set of m. So this is actually m itself. So GCD of m and 0 is nothing but m itself. Okay, and similarly, another important result which you can discuss is that suppose you have to find out the GCD of m comma n. Okay, so GCD of m comma n. So you have to, so basically, suppose D is the GCD of m comma n. That means D will divide m as well as D will divide n. Okay, so you can conclude that D will divide m plus n. Why? Because m will be equal to some c into D, n will be equal to some some t into D. So m plus n will be equal to c plus t into D. So you can see that GCD will, or the common divisor will be dividing the sum, the differences, maybe the linear combination. Okay, maybe am plus q, and that also it will be dividing because of this result. Okay, so it will be a c d plus q into td. So GCD will be divided, or common divisors would be dividing the sum product, sum as well as the differences, the linear combinations of m and n. Okay, in particular, it will be dividing this m minus qn. Okay, so GCD of mn will actually be equal to GCD of m minus qn n. How? What do you mean by that? What do you mean by that? What is the significance of the result? So if you think your m is a bigger number, so if you divide m by n, okay, what will you be getting? You will be getting a quotient as well as a remainder. So your m can be written as q into n plus r, or m minus qn will be equal to r. Okay, so the significance of this result is that it is obvious that if a divisor D divides, if a number D divides m and n, it will always be dividing m minus qn and n. Why? Because if D divides 7, D should divide m minus qn. Okay, because D is present in both this m and n as well as n itself. So GCD of m and n will always be equal to GCD of m minus qn and n. Okay, because of this linear combination result. Now the significance of the result is that this GCD of mn will be equal to GCD of m minus qn, or it will actually be equal to GCD of n comma the remainder. Okay, so that means a bigger problem. So if you have to find a GCD between two big numbers, GCD between, for example, 3, 2, 5, 6 and 1, 2, 3, 4, what you have to do is you divide this 3, 2, 5, 6 by 1, 2, 3, 4 and you take the remainder then it will be 1, 2, 3, 4, comma, remainder. Okay, so you can reduce the bigger problem into a smaller problem. Okay, so that is the significance. So again, if you have to find the GCD again, you divide the 1, 2, 3, 4 by this remainder. Then the next step, it will be same as the remainder into the new remainder. So the bigger problem is again actually you have reduced to a smaller problem. And this algorithm of finding the GCD successively is called Euclidean algorithm. Okay, so Euclidean algorithm will help you to reduce the task of finding GCD successively. Okay, let us illustrate this result using, let us try to find out a simple problem. Let's just find out the GCD of 34 and 13. Okay, maybe you can guess the GCD of 34 and 13, but let us find out. So let us find out the GCD of 34 and 13. What I told is that first to divide this 34 by 13, what will you get? It will be 2 times 36, the remainder would be to 8. Okay, so what will be that? So this will be equivalent to the GCD of 13 comma 8. So you divide this and you take the remainder, that will be equal to that. Again, you can reduce the problem further. You divide this 13 by 8. Okay, so you will be getting the remainder as 5. So this problem can again be reduced to 8 comma 5. Right? Again, suppose you roll on GCD again. Again, you repeat the same process. 8 by 5. It will be 5 and 3. So this problem will again be reduced to finding the GCD of between 5 and 3. Okay, so that is the GCD of m and n is same as GCD of n comma m minus qn, or it is same as GCD of n comma r. Okay, so GCD of mn is same as GCD of n. So if you switch it also, it's the same thing only, it's symmetric. So GCD of m and n is same as GCD of n comma n minus qn or n comma r. So next step, you will be GCD of r comma remainder when this r is divided by r. Okay, so you divide this n by r and take the remainder, and then you will be getting. Okay, so you can successfully find it out. So again, so here also 5, 3, it will be simply that. So how will you find 5 and 3? You divide 5 by 3, it will be there, remainder would be 2. So it will be reduced to 3n comma 2, right? And again, so 3 if I divide by 2, it will be 1 again, 2 here, 1. So it will be reduced to 2 and 1. Okay, and again, if 2, if I divide by this 1, it will be 2 times 0. So it will reduce to GCD of 1 comma 0. And you know that GCD of m comma 0 is nothing but m itself. So the GCD is finally 1. So this is how you perform Euclidean algorithm sequentially. Okay, that way thereby reducing a bigger problem. So these numbers are very small just for illustration purpose, but you can use this result for any big numbers also. You can use this successively by dividing and finding out the remainders. Okay, of course this method is not efficient. There are much more efficient methods to find GCD, but this is the basic method which is the base of all those efficient methods. So that is why we are teaching it. Okay, now one more significance of this algorithm is that you can actually express the GCD as a linear combination. GCD of any two numbers as a linear combination of m and n. That means I can write it as some am plus bn. So, okay, so you can always express GCD as a linear combination of m and n. Okay, for example, in this case itself, let us try to do that. Okay, so here 34 and 13. So this is actually 34 is equal to 13 into 2 plus 8. So 34 can actually be written as 1 into 34. So I am going to write every number in this sequence as a linear combination of 34 and 13. So this will be written as 1 into 34 plus 0 into 13. It's a trivial thing. And similarly 13 can be written as 0 into 34 plus 1 into this. So these are basically three trivial representations. Okay, now the next number in the sequence was 8. 8 can be written as 34 minus 13 into 2. So you can see that 8 is written now as a linear combination of 34 and 13. Okay, now the next number in the sequence was 5. So how will you write 5? So basically 5 you obtain from this here. So 13 was written as 1 into 8 plus 5, right? Now 8 is written as 1 into 34 minus 13 into 2 from this result. So plus 5. So this will be, if you take this to the other side, it will be 3 into 13 minus 1 into 34. This is how you write 5. Okay, so I have written a step for 5 also. For 8 also I have expressed a linear combination. The next number in the sequence was 3. Can you write down how to write 3 here? So again 3 also you can do in the same manner. So 3 you obtain by dividing 8 by 5, right? So 8 is actually 1 into 5 plus 3. So 8 also you know how to write. 8 is actually 1 into 34 minus 13 into 2, and 5 is actually 3 into 13 minus 1 into 34 plus 3. Now can you tell me how to write this 3 here? So when you bring in the other side, it will be 2 into 34, right, minus 5 into 13. 2 into 34 minus 5 into 13, that is how you write 3. Okay. So the next number in the sequence was 2. So how will you write 2? So 2 was obtained when you divide 5 by 3. So it was 5 was written as 3 into 1 plus 2. So 5 already know how to write. How will you write 5? 5 is written as 3 into 13 minus 1 into 34. That is equal to what is, how will you write 3? 3 is equal to 2 into 34 minus 5 into 13, right, plus 2. So now tell me how to write this 2. Now 2 can be written as, bring all these things to this side. So it will be 8 into 13 minus 3 into 34 is equal to 2. 8 into 13 minus, so correct me if I am wrong. So 8 into 13 minus 3 into 34 is equal to 2. So every number I am writing it as a linear combination. Finally, I have my 1. How you obtain 1? 1 is obtained by dividing 3 by this 2. So 3 was actually 1 into 2 plus 1. 3 you already know how to write. How will you write 3? 3 is nothing but 2 into 34 minus 5 into 13. That is how you write 3. That is actually equal to 2 I have written as 8 into 13, right? 8 into 13 minus 3 into 34 plus 1. So finally you are getting the linear combination in the form of 1. So it will actually, when you bring it here, so it is 5 into 34 minus 13 into 13. Okay. So that is actually equal to 1. Can I verify what is 5 into 34? 5 into 34 is 170. 13 into 13 is 169. So this is verified. So you can see that our GCD of 34 and 30, GCD of 34 and 30 was 1. So this 1 can actually be written as a linear combination of, so maybe some lambda into 34 plus some mu into 30. So a very important result. So basically in this case it was 5 into 34 minus 13 into 13. So this essentially means that any common divisor of this 13, 4 and 13 should actually divide this one. So when you represent this as a linear combination, so you can see that any common divisor of both 34 and 13 will be dividing this linear combination also, right? So it should be dividing this one also. Okay, so there is no other common divisors other than 1 which can divide this one. So only 1 is the common divisor here. Okay, so the very important result, like GCD can always be represented as a linear combination of the other two numbers. Okay, so that was some important results we have discussed here. So we can always find two numbers for GCD which is lambda m plus un is equal to 1. Okay, and in particular case, you will say that two numbers are relatively prime if GCD of a comma b is 1. Okay, for example, our numbers 34 and 13 were relatively prime because the GCD of 34 and 13 is 1. Remember that they are not prime numbers. For example, 13 is prime but 34 is not prime. Relatively prime means they both do not have common factors except this one. Okay, for example, the GCD 4 and maybe 9 are relatively prime. They don't have common factors except this one. Okay, but 4 and 6 are not relatively prime because they have a common factor of 2. Okay, so similarly, if the numbers are relatively prime, what can you say? You can find, so if a and b are relatively prime, what can you say? I can find x1 comma y such that ax plus by is equal to 1. This is obtained by the property of GCD, where GCD can be written as a linear combination of a and b. That's the idea. So if it's relatively prime, I can write a comma b as ax plus by. Why? Because your 34 and 30 was relatively prime, so I could write 34 and 13 as 34x plus 13y is equal to 1. And in our case, we found x was 5 and your y was minus 13. That's it. Okay. So if it is relatively prime, remember this result, it can be written as ax plus by is equal to 1. Okay. Now let us discuss a small significance of this result. Look at this one. Okay. Suppose that a divides bc. Okay, suppose a divides bc and a and b are relatively prime. You have to show that a divides c. Okay, so what do you mean by this? For example, let us say, suppose a and b are relatively prime. What do you mean by that? It means ax plus by is equal to 1, right? Since a and b are relatively prime, GCD of a comma b will be equal to 1. That means I can write it as ax plus by is equal to 1. Okay, now I have to show that a divides c. Okay, so I have to show that c is a multiple of a. So what I'll do is that in this equation I'll multiply uniformly by c. So what will I get? It will be acx plus bcy is equal to c. ACX plus BCY is equal to C. Now if you look at the left hand side, you can see that A is a factor of ACX, and also it is given that A divides BC. That means this is actually A into some factor, A into some multiple, right? So A is a factor of ACX, and also A divides BC means BC is a multiple of A. So I can write some A into something here. So in the left hand side it will be A into some multiple which is equal to C. So you can see that A is a factor of C, or in other words A divides C. Okay, so A divides C, that's the case here. Okay, so this will only work if they are relatively prime. If they are not relatively prime, this will not be working, right? For example, yeah, so suppose 4 divides 6 into 2. Okay, so 4 divides 12, that's true. Okay, now that doesn't mean that 4 divides 2. Why? Because you can see that 4 will not divide 2 in this case, because the problem here was 4 and 6 were not relatively prime. There were some common factors. Okay, this result will only work if your A comma B were relatively prime. Okay, only in this case it will be working, otherwise it will not be. So think of some counter examples to this result. So you have to be very careful when you discuss the results relating to number theory. Always search for some counter examples, some simple examples, right? Okay, moving forward, let us look at some more results also. So if A and B are relatively prime and A divides C and B divides C, then AB divides C. Again a result for relatively prime is only. So before you prove this result, remember what happens if they are not relatively prime. Just check. Okay, so before that let us try to look at this. So it is given that A divides C. Okay, so A could be written as so C can be written as some multiple of A, right? So C could be written as maybe some A into X, and again C could be written as some B into Y. Okay, C is a multiple of, so A divides C, B divides C means they are multiples of this X, B, A and as well as B. Okay, I have to show that AB divides C. I have to show that C is equal to AB into some value. Okay, maybe some Z. I have to find a relation like this. That is what I am going to do here. Okay, so before that it is given to you that A and B are relatively prime. Okay, so A and B are relatively prime means AX plus BY is equal to 1. Okay, this is known to us. Okay, so I am not using this AX plus BY because already we have used a notation of X and Y here. So let us just erase that. Okay, since already I have used this notation here, I am just erasing this thing here. Okay, yeah. So since A and B are relatively prime, I can write lambda A plus maybe some mu into B is equal to 1. Okay, so what I'll do is that I need to obtain this result. Okay, so I'll start with C. So C could be written as C into 1, right? Very simple result. So this is actually C into lambda A plus mu into B. Right? I have replaced it by this result. So this is actually C lambda A plus C mu into B. Okay, now I am going to bring AB into this picture. I'll bring AB here. So that I could write this as some AB into something. Okay, for that I am going to introduce AB here. So for that I will use this result. C is actually equal to BY. So this is actually BY into lambda A plus this is actually AX into mu B. So I can take AB outside. So this will become Y into lambda plus mu into B. Okay, so you can see that C is actually AB into some Z. So C is actually some AB into Z. That means AB divides C. So this was obtained by because of this result only, since A and B were only relatively prime. Otherwise we will not be obtaining this result. So you are adjusting the coefficients based on that result. Okay, so please go through it once again and try to do it by yourself. Okay, so if it is not relatively prime, this will not be true. Okay, so for example, yeah, but 6 divides 12 here. I also 3 divides 12. But 6 into 3, 18 will not divide 12 because 6 and 3 were not relatively prime. So this result is given here. So if they are not relatively prime, this result will not hold. So you have to be careful here. Okay. And similarly, can you look at this result? Try doing this result. If A and B are relatively prime and A and C are relatively prime, then A and B, C are relatively prime. So it is given to that GCD of A comma B is 1. Also it is given to you that GCD of A comma C is equal to 1. I have to show that GCD of A comma BC is equal to 1. Or I have to show that I could write it as some AX plus some BC into Y is equal. I should obtain a relation like this. So only then you can say that GCD of A comma BC is equal to 1. Okay. Now GCD of A comma B is equal to 1 means you can write some AP plus BQ is equal to 1, right? GCD of A comma C is equal to 1 means I can write some AR plus CS is equal to 1. Now we multiply both of them together, both LHS and RHS. So it will be AP plus BQ into AR plus CS, which is equal to 1. When you multiply it, what will you get? It will be APAR plus APCS plus BQAR plus BQCS. So you can see that there is A into some factor. You can take A here plus BC into QS is equal to 1. So you can see that some A into X plus some BC into Y is actually equal to 1. That means A and BC have GCD 1. Okay, that's the idea here. So A and BC are relatively prime. Okay, so these were some important results regarding this GCD. So we will deal with Chinese remainder theorem in the next lecture. Okay, thank you.